So, good afternoon, everybody. Thank you for the invitation and for the introduction. And let's get started. So this basically has been already said. So just to give you a little bit of the context, the PhD I've done with Rolf Pfeiffer, who is basically one of the proponents of embodied cognition. And back then I was working on this dog robot and how this kind of quadrupedal creature can develop its first models of its body and learn a little bit about the world from scratch, basically. And then I realized that I'll be more interested in basically in modeling like a real thing. So this dog was a kind of creature that, like an animat, like not a real model animal. And I realized I would be more interested in modeling actual brains and actual babies, how they develop. That's why I joined the ICAP facility, because the ICAP humanoid robot is basically, in my view, the best platform to study developmental robotics. And as of the past 5 years, I joined the Department of Cybernetics here at Karlovo náměstí. So this is my team currently with 2 postdocs and 7 PhD students, and these are the robots we have. So I'm very proud that it's almost 1 year now that we have this ICAP humanoid robot. So that's a robot that is like a 4-year-old child with a whole body sensitive skin, and you can come visit and see it. We have some other humanoid robots, and we have also some collaborative manipulators, so manipulators that can share the workspace with humans. Okay, so the main topic is really the body models. So how we as engineers model robot bodies, and then we get to how the brain represents our body, and we will draw some interesting parallels and inspirations for how to make robots better. So the traditional way is that there are mechanical engineers, they have their CAD models, and then that basically provides the basis for all the models that we use to control the robot, like kinematic models and dynamic models. Taking the ICAP as the example, each of those modules is basically a software library. So there will be an ICAP models generator, then there will be the models, and then there will be individual libraries that deal with all the things that roboticists need to deal with, like forward kinematics, inverse kinematics, state estimation, movement planning, movement execution, and they would draw from these individual libraries. So that's a very traditional engineering design. Here is an example of the classical David-Hartenberg representation of a kinematic chain. So for the ICAP upper body, this would be the kinematic parameters. Now, so this traditional way has some pros and some cons to it. So it's quite neat. There is a lot of mathematics and physics, which is also neat, and that leads to nice properties like extrapolation. It's a very veridical representation, meaning that that's really how things are, that it represents the truth. So basically the model represents the physical robot. It's kind of its replica. So we understand the model, and we can measure the accuracy. So we can compare in the model how long is this segment, and then we can measure on the physical robot, and we know how good our model is. It's modular, which is another convenient property. For example, because of maintenance, because if one thing is one isolated module in one place, and then you improve that module, then everything will automatically draw on the newer version. The cons would be that there's a lot of man hours basically involved in the whole process of constructing and updating such a model. The model would typically be fixed. If you want to update it, you typically draw on some external calibration procedures. And there is no redundancy, which could be a good thing. But at the same time, this I claim basically leads to fragility of the whole system, and it's very different than how it's done in biology. Robot body models and calibration. So so this would be a simple manipulator, and with 3 joints, and this would be the forward kinematics of such a manipulator. And this is the model. This is the robot. This has some properties. So typically it would be fixed, centralized, meaning there's only one place where this model lives. It would be explicit, meaning that if I look at this A3 here, then there would this corresponds directly to this link or length of this link. Rely on minimal sensory information. So in this case, the only sensory information that is present is the joint angles. And it starts from significant prior knowledge, such as from the CAD model, for example, you would initialize all these parameters. Calibration typically performed using external metrology, like a Leica laser scanner, for example. And the calibration is actually like a mere fine-tuning of parameters. So the traditional method, for example, described in this book chapter in the Handbook of Robotics, so John Hollerbach is one of the big figures there. They distinguish open loop calibration, which is when you're using a visual system such as a laser tracker to observe some components of the pose of the robot. So manipulator is not in contact with the environment. Or there are what they call closed loop calibration approaches, when there is a constraint, such as you fix your end effector and some of the components of the pose, like if you fix it completely, or you know that there is a constraint that you're touching a plane, and you use these constraints again for calibration. Now with robots like humanoid robots, social robots, with robots in general nowadays, the trend is that they become cheaper and use more elastic materials. But on the other hand, that of course compromises accuracy. So that's a problem. On the other hand, they come very often equipped with affordable but increasingly accurate sensors. A lot of cameras, a lot of tactile sensors, force sensors, inertial sensors. This is the Pepper robot, and you see that this is really equipped with a lot of sensor, and that's not a very expensive robot. On the other hand, it's all from plastic essentially, so you cannot expect a big accuracy. So these two factors together, they create a necessity and an opportunity for autonomous continuous recalibration. So using all those sensory modalities, the robot should be capable and has to be capable of basically continuous recalibration that is self-contained by exploiting the onboard sensors. So this slide provides an overview of a number of case studies that we did in this basically in this direction. So what you see here is the iCap robot performing self-touch. So iCap has this whole body skin. So you see the activations when it's tickled on the forearm, and then it goes at reaches there and also looks there, and this creates redundant information. So you're closing a different kinematic chain. So the left forearm with the skin activation, if you have the skin calibrated and you have the forward kinematics, you know where that point is in space. The same goes for the other arm, so the tip of the right finger that is touching there. So you can exploit these constraints to fine-tune the model. So this is one way of self-contained calibration through self-contact. The same is that you can also look at the same place, which is, for example, also happening here. And then by using the two eyes, either by projecting into them individually or by using stereo vision, you would have one additional piece of information about where that point is in space. So the idea here is that these are the self-contained calibration approaches that can be combined in different ways to calibrate the kinematic model of, in this case, of the robot, but not only the robot kinematics, but also the placement of the sensors. For example, if you get a new sensor, you can use it in this way to calibrate the robot without any external device. Here is an example of a now robot that's kind of the opposite of what was happening here. Here we had the skin calibrated, but we were updating the kinematics. Here we received a robot with brand new skin, but we had no idea where in space the individual tactile sensors are. So we used the self-contact and the forward kinematics to calibrate the spatial position of the individual tactile sensors. And yeah, there is also a toolbox that is freely available that can be used for all this kind of multi-sensorial, multi-chain robot calibration. Okay. So yeah, this is just a schematic illustration of these different methods. So this would be the self-contact. There might be some offset if there is something that, let's say, the skin has a certain width, for example. This would correspond to the situation where you have let's say one hand of the robot and you're looking at your own hand through the cameras. And this would be a situation where you're looking at two hands that might, so that would be looking at two hands. And those may be in contact at the same time, so then you might combine all these chains. The methods that we use for this calibration are quite standard. So basically, this is a nonlinear least squares optimization. The only thing you have to do in addition is you need to find a way how to combine these different chains. So they might, sometimes the error would be in centimeters, sometimes it would be in pixels if you have the reprojection error. Also, there might be different uncertainties. So, corresponding to the different ways of connecting the chain. So, for example, let's say the vision might have problems in depth, while the self-contact may have, other inaccuracies. So this is something that you can all incorporate into a joint optimization function with some scaling factors. And and you can do it basically pairwise, or you can do everything together. And it actually works nicely. Also, we showed that the identifiability and observability of the parameters is better. So there is some kind of synergistic effect of using these multiple chains at the same time. But still, it is quite laborious. This whole thing. It's a local optimization method. You need typically a good initial guess of parameters. And it will not cope with dramatic changes, like if suddenly one arm is double the length. This is not what. So the method is not ready for these kind of things. So that concludes the part kind of how we extended the standard robotics models, to make them with self-calibration that is self-contained, but we have basically the ambition is to do much more than that, to be able to cope with dramatic changes and to really lead to some resilient machines. So these are two notable examples from the literature how robots can cope with dramatic changes, such as you block one leg of the robot. This is the work of Josh Bongard. So there is a physical robot and there is a simulated robot. The simulated robot is the model of the robot. So the model is basically a replica of the robot in ODE, including the motors and the sensors. And the robot is currently trying to figure out, based on the sensory readings and the motor commands from the real world, what could be its best model. Once it figures it out, it can use it to generate a gate. And eventually, if you, for example, block one leg of the robot, it can use this same method to compensate and find a gate in this new situation. So that's something that we would like to have. This is more recent work, but essentially the same idea from Antoine Coulis and colleagues. And so that's something what we would like to have. But these are basically still toy examples. So it's probably not a coincidence that these robots have a particular morphology, and and this is basically what you can do there. But it's not something that you can now do with, let's say, a humanoid robot. A quick overview of some, works, like more recent works where, that obviously employ deep learning. This is work from ETH Zurich, from Marco Hutter's group, where the animal robot model is a kind of hybrid model that involves some rigid body modeling, something that that capitalizes on knowledge in robotics, but some things that you cannot model, that you basically need to learn them with a black box model, like the actuator dynamics. You can put this together, and they actually have a very realistic simulator where they can train gates that are easily transferred to the real world. So this is another possibility of how you can model your robot. Other influential work is this one from DeepMind, how this whole horde of manipulators is training to grasp. Let's forget about the body model. So there is no explicit body model. Well, in fact, the mapping that is learned is basically from visual inputs to the sort of movement the arm should do in Cartesian space, and including what the gripper should do. But there is the robot inverse kinematics and control that's not learned, that is still used, because that for that we have a very good model. In general, the advantage of these kind of approaches is that it is learned and it's possibly adaptive, even though like relearning, adding something to something that has been learned is not easy. Fewer man hours, unless you need to do some hand labeling. On the other hand, the disadvantages would be that it's for one task. It's black box, meaning that it can be fragile. It's a danger of overfitting. It would typically allow only interpolation. We have a limited understanding of the model, and it's difficult to maintain. Plus, there are many simulator, or in this case, real robot hours, and typically many GPU hours too. There are some works that basically aim to for generalization. So this is one example where the model is regularized by simultaneously learning a forward and an inverse model. This is some other work where they use a variational autoencoder on the ICAP robot without learning any specific task, but basically the robot just doing babbling, and they are learning basically to represent this sensory motor space across many modalities. So yeah, I guess many have seen this DARPA robotics challenge, how all the poor humanoids are falling, and this is without any anything breaking. So it just shows that the state of the art is basically still not there. So the resilience is really something that is largely missing here. So let's look at animals and brains for inspiration. So one aspect is animals are good at tool using, and so this is an example that a crow is not only using a tool, but it's actually also making a tool to make it a better tool. And crow being a relatively simple animal, this is quite impressive. So tool use, body extension, so that's something that we need to be able to cope with. And yeah, robots are really, not in a position to get a new tool and do something meaningful with it. Resilience, you have these amazing animals that, for example, are born without 2 legs, and they can find strategies how to locomote. So that's the adaptation to injury and resilience. So that's another target. And this is an illustration of the awareness of body in space. So this is an elephant that was trained to take this rug off the ground. And you see how it really naturally realizes that it's standing on the rug, so it just steps away and then it can lift the rug. So so this is and this is not something that is very easy to model. So lesson one is that there is a lot of plasticity, or that's how it's called in neuroscience, or adaptivity, and few constraints. One example is this famous Pinocchio illusion. So if you hold your nose and there is like a vibrator on your biceps tendon, you get the illusion that your arm is extending. And actually, people get the illusion that their nose, because there is this contact, is extending. So you get the illusion that your nose is, I don't know, 30 centimeters long. So that's something that is quite intriguing, and it's not something that we would expect from the robot models that we have. But maybe that's something that we simply have to reconsider, that basically we have to make our models more adaptive and more liberal in a sense. Yeah, the octopus is another case in point. People know that it's a highly intelligent animal, yet basically there are no central representations of its body. So there is no like there is no homunculus, so there is no octopunculus. So according to these researchers, the way the octopus initiates the arm movement to eventually catch the prey goes as follows. So it initiates a bend in the arm so that the suckers point outward. It orients the base of the arm in the direction of the target, and then it propagates a bend along the arm, and it can like activating all the muscles, and basically it terminates the movement as soon as the suckers touch something. So there are 3 kinematic control parameters, and keep in mind that this is basically like it has an infinite number of degrees of freedom. So this muscular hydrostat, it's really much more complicated than a 6DOF robot arm. And still we have really, so inverse kinematics is basically still a challenge, for, let's say, for example, for a humanoid arm. And so obviously the octopus is choosing a completely different strategy. So it's much more reactive, much more initially feed forward, and it would rely on the feedback once it basically contacts the prey. So that's very different than how robot reaching and grasping works today, where you basically perceive the world and you blindly send the gripper, and then you hope that you're in the right position when you're closing it. So it's a very different approach. Lesson 2 from the octopus is that you can use the body directly whenever you can. So basically, whenever you can, you don't need to go through the model, but when you can use the body directly. So the octopus is really has this, you can offload a lot of functionality to the musculoskeletal system or to the peripheral nervous system, like in the octopus, which goes back to Rodney Brooks and the world as its own best model. And yeah, the challenge here is whether the same can be applied to the body. So the body is also always there. So the question is, how much and when do I actually have to go through the model, when I can always feel my body or look at my body. So I may not need to represent all of it all the time. However, in the brain, there clearly are body maps, and there's a huge literature about it. It's not really converging. There's a lot of empirical evidence, but there's very little, let's say, there are very few models. So the knowledge how the brain represents the body is still kind of fractured. I'll now compare on some axes the robot body models with how the brain represents the body. So as we started, so this toy example of the robot manipulator and its forward kinematics, this would be a fixed explicit model, and that would be unimodal because there are these joint angles that come in. And yeah, we expect something completely opposite, the opposite characteristics from the body models, body representations in the brain. So we expect them to be adaptive or plastic, implicit. So for example, just like here, this A3 is this length here, it would be hard to find a neuron that represents the length of your forearm. So that's for implicit, multisensorial or multimodal. So that's clearly a property of brain-like representations. And yeah, so this would be the axis here. And so the kind of the mission for my research is to, you know, bring these robot models more in this direction. On one hand, to understand the mechanisms of the biological body representations that we don't understand, and also hoping for better performance of robots in terms of autonomy, robustness, and safety. So, you know, and as humans and animals manifest all the time. So going back to some of the examples that we briefly mentioned. So this traditional model would be, you know, fixed, and there are no A model, so without any sensory inputs, because it's a direct basically geometry of the robot. Now the brain is the complete opposite end of the spectrum. It's like massively adaptive and multisensorial. And then the other works would fall somewhere in between. So this, for example, this work with the ICAP self-calibrating, you know, it's making it adaptive, and it's using 3 modalities. Yeah, this uses even more modalities. These works, for example, by Bongard or by Sturm, yeah, they are even more adaptive. They can cope with failures. So, for example, you know, when you block one joint, so that's something that the other models typically cannot do. There can be other axes that are perhaps less straightforward. One is the modularity. So the engineering models are highly modular, while the, for example, the deep learning models would be more end-to-end and holistic. So it's impossible to dissect, you know, which part represents what, which is perhaps similar a bit to the octopus, where it's also very, and the other axis that is, you know, somehow similar is just distributed and specialized. So these models are clearly specialized on one thing. They are, you know, end-to-end for one task, and the functionality is distributed. So that's also the case for the octopus. The human brain would not be at this extreme, the other extreme, but will be somewhere in between, because there clearly are regions of the brain that, you know, that represent certain properties of the body and that are used across tasks. So the brain cannot simply afford to have an end-to-end. It has many neurons, but it cannot afford to have an end-to-end solution for every task. So that's why basically it sits somewhere in the middle, with basically consolidating some representations that can be reused for certain tasks. Yeah, indeed, there's also this body image and body schema distinction, body schema being like the sensory motor kind of low-level representations for action. Body image would be more like visual based or even semantic, that you can name your body parts. You know, this is my forearm. If you close your eyes, you can imagine how your forearm looks like. So this is body schema, body image. Explicit and veridical, it's for the classical robot model. Implicit embodied would be the octopus case. Parallel and recurrent, that's again the brain, and serial would be the robots. Okay, so these are kind of this is another way of looking at the spectrum of where you can be with your models. And this is a case study that is quite prominent in psychology. So there was a person whose name was Ian Waterman, who lost the tactile and proprioceptive afferent. So basically, he was not feeling his body, he was not feeling touch, he was also not feeling proprioception, like where his body is in space. Still, he learned to to operate in the environment by basically looking at his hands and looking at what he was doing. He was very slow and very clumsy, but still he could basically cope with all the tasks he needed. And in some ways, I think there's a lot of similarity in how this man functioned with how robots work, because they are basically the same. They have to watch and update the model, and they are very clumsy. So he actually had to basically work like robots. For example, when grasping, he had to constantly monitor what he was doing, which is not how we normally operate. Normally, you just send a little bit like the octopus. You just send your arm somewhere, and then you make contact with the cup, and then you can grasp it. I'll briefly show like 2 case studies, like how we're making progress in making these brain-like robot body models. One case study is we for the ICAP skin, we basically wanted to learn the body map, the tactile homunculus, so how the skin of the robot is represented in its brain. So this is the human or monkey homunculus. So it's a part of the cortex that basically has this famous distorted somatotopic organization. And so for the ICAP, ICAP doesn't have skin on the face, so we just took the parts where it has skin, and we used a self-organizing map so basically I was stimulating the robot for like, I don't know, 3/4 of an hour with my thumb being bigger than an individual tactile sensor. So from the correlations of the simultaneous co-activations of the sensors, the cohort map can figure out which taxels are next to each other. This problem is not constrained enough. So basically, every time you run it, you would end up with a different arrangement of the ICAP cortical sheet on the output layer of the SOM. So that's why we needed to modify the SOM if we wanted to obtain the same topology and the same coarse somatotopy like in the human or monkey brain, which is basically also what is genetically predetermined. So we modify the SOM to impose additional constraints on the receptive fields, and then we let the details be found by the algorithm. And this is what we obtained. These are receptive fields of individual neurons for the torso. So this neuron, this is its receptive field. It's sensitive to touch on this area of the torso, and you see that the somatotopy is preserved. So this is only one building block that we have a brain-like representation of the robot skin. Of course, this in isolation is not like so useful. So our next step is basically tactile proprioceptive representation. So what is called somatosensory in neuroscience. So how you combine touch and proprioception to learn that your body is something like an object in space. So the hypothesis is that there is like spontaneous self-touch in babies, and the brain is detecting these motor, proprioceptive, tactile, potentially also visual correlations. And it may find these events interesting because they are redundant. So it's like a food for the brain in the sense that it can exploit these redundancies to learn. And so we're making models that should do that. So basically, the robot, in this case, the simulated now robot with the skin, should actively explore in an efficient way such that it discovers the skin space, which essentially is learning some kind of inverse kinematics. So basically, we then test it whether it can reach for different, when we, let's say, like tickle it on different parts of its skin, we're testing whether it can reach there. There are different models. Of course, the motor babbling, which is like, a random walk in joint space, is going to be highly inefficient. But there are much more smart models that basically monitor the learning progress of the inverse model in different areas, and it always focuses the attention to this sub problem where it's currently making the biggest progress, and then you can be much more efficient in how you basically learn this mapping. The sporadic touch, meaning that you're basically always restarting from the home position. well, complex touch, something that was observed also in babies, is that you basically stay in contact with the skin, and that seems more natural to explore and more efficient in that way. Okay, so coming to an end, what from brain-like control or from or body models should the robots take on board? So should we learn tasks or body models or physics? So there is a paper by Lake et al. That's from Josh Tenenbaum's group. The human brain cannot afford an end-to-end network for every task. That's why it developed body representations. Some characteristics of brain-like body models should clearly be incorporated, and it should be largely unproblematic, like the adaptivity, or basically the self-calibration, or the multimodality. Okay, so on this axis, we can make, let's say, natural progress. Now, some characteristics of brain-like body models are clearly at odds with engineering practice. So if we, giving up modularity or the centralized and universal nature of the models, or their explicit and veridical character, or serial operation, is going to be very hard. But at least that's my vision and mission currently. I think that's what we need to do if we really want to go for versatile, resilient robots. So in the end, humans and animals' body models, they serve action, and they don't need to be correct. They need to be useful. So it doesn't matter if it's not like physically correctly represented in our brains. And the brain always has many suboptimal redundant solutions at hand, and this gives the robustness. So I think we should shift from accuracy and optimality to basically many suboptimal solutions, but some of them will always work. So most of what I presented is written up in these two recent book chapters. One is more like for the audience in psychology and neuroscience, and one is for a robotics audience, if you're interested in more details. And with that, I thank you for the attention.